Hello everyone and welcome to week 5. In week 5 we will start with this powerful concept which is called as transfer learning. Transfer learning is a research problem in machine learning that focuses on storing knowledge gained while solving one problem and applying it to a different but related problem. It is a machine learning method where a model developed for a task is reused as a starting point for a model on a different task. Now, we know that as a human being, we have this inherent ability to transfer our knowledge across different tasks. What we acquire as knowledge while learning about one task, we try to utilize it in some way to solve a different but a related task. And of course, the more related the tasks are, it is easier for us to transfer or cross-utilize these knowledge. For example, if you know how to ride a bicycle, it becomes easier for you to learn how to ride a motorbike. So, know how to ride a cycle, it implies that learn how to ride a motorcycle. Or, if you know how to do a math and stats problem, if you are good at mathematics and statistics, it becomes easier for you to learn machine learning or deep learning because you are able to transfer your knowledge about mathematics and statistics very easily to a machine learning problem. Or if you know how to play a classic piano, then it becomes easier for you to learn how to play a jazz piano. So this itself is the concept behind transfer learning. Utilize your knowledge in one task to solve a problem to solve a different problem or to solve a related problem, right? So in these 3 examples that I have just mentioned, we are not actually learning everything from scratch, but instead we are transferring and leveraging our knowledge from what we have learned in the past to do something new. And this idea of transfer learning is actually a one step towards artificial general intelligence or AGI. So we already know that there are 2 types of AI, one which is the narrow AI and one which is the true AI. So currently we are in this in the era of narrow AI, which means a model which is developed exclusively to solve a particular task, right? For example, a model for sentimental analysis. So that model only works to perform a sentiment analysis. Whereas what we are trying to achieve is this concept of true AI, or what we call as artificial general intelligence, which is able to solve any problem given to it. And it is believed by the research community that this idea of transfer learning is one step towards our artificial general intelligence, or what we call as true AI. The research community of computer vision is very progressive, and they actually post a lot of data set in the internet. For example, we have the image data set, the COCO data set, the Pascal data set, and there are many more data set that is available also in the Kaggle community. So many researchers have taken these data set and have trained their algorithms, like some of that which we have already studied: AlexNet, VGG16, LeNet, Microsoft ResNet, GoogleNet, and so on. Right? So many researchers takes these data set which is available in the internet and have trained their algorithms on it. And sometimes these training can take several weeks or months, and even might require more than one GPU. And of course, we know the end product of this training is actually the learned parameter, right? The weight and the bias, that is what is the end product of a training. So we can use this weight, which after maybe days of training someone has figured out, and use that to initialize our own deep neural network. Right? So that is the idea of transfer learning. Rather than training our model from scratch, trying to utilize what is already available and what we already know works well for something. Right? For example, when we were building our first convolutional neural network, the first thing is that we need to do a random initialization of the weight. Right? And from that random initialization during the learning or the training process, your model becomes more and more closer towards the actual weight and bias. So one idea of this transfer learning is to use a available weight, a pre-trained weight from a different task to initialize a problem that you are trying to solve, which is a related problem to your original task. So rather than doing a random initialization, what I'm doing is I'm initializing my model with a pre-trained weight, which you might have obtained from a research community. So I am transferring my knowledge from some of these very large public data set to my own problem, probably for which I might have a smaller data set. So one key motivation, especially in the context of deep learning, is the fact that most models which solve complex problems need a very large data set. And gathering such a huge labeled data set for a supervised learning model can be very difficult as well as costly. And of course, we have this ImageNet data set which has millions of images. However, getting such a data set for every domain in the computer vision problem is really challenging. So there is a huge difference between this traditional approach of building a machine learning model and using a methodology following transfer learning principle. And that is well replicated in this figure you could see. So you can see that the traditional learning is very isolated and it occurs purely based on a specific task, a specific data set, and a training which is separately isolating these models. So no knowledge is retrained or reused which can be transferred from one model to another. Whereas, so as you can see in this figure, I have a data set 1 which is used to train a particular model, a different data set to train a different model, and there is no interaction between these models, right? It's a separate, isolated task. Whereas in transfer learning, you can leverage the knowledge, which is nothing but the features or the weight from the previously trained model for actually training a newer model. And probably for that newer model, you might have even a very small data set. So clearly there is an interaction or a transfer of knowledge happening between these two models. For example, let us assume that our task is to identify the objects in images within a restricted domain of a classroom. Right? So I have this computer vision problem wherein which I need to identify the objects in an image in a restricted domain of a classroom. So let us call that to be, say, task T1. Now, given this data set for this task T1, we can train a model and tune it to perform well or generalize well on unseen data points from the same domain, which is the classroom. Now, suppose you have a different problem now. So you have another problem, another task which I call as, say, T2, wherein which we need to detect objects from images in a restricted domain of a restaurant. Now, ideally, we should be able to apply this model which we have trained for T1 to our new task T2. Ideally, it should work, but in reality, it actually has a performance degradation when we try to fit our model for T1 to do this task for T2. Now, this is where your concept of transfer learning will come into play and will enable us to utilize the knowledge from our previously learned task, which is, of course, T1, and apply it to our newer related task, which is T2. So if we have significantly more data for task T1, we may utilize its learning and generalize its knowledge, which is features and weight, for our task T2, which might significantly have a less data. So why this will work is that, why the concept of transfer learning will work in this case of computer vision task is that certain low-level features such as edges, shapes, corners, intensity can be easily shared across different tasks and thus enable knowledge transfer among the different tasks. So that is the main idea behind transfer learning, to use something which we already know to a different task. There are two common approaches to deep learning. The first one is developed model approach, and the second one is pre-trained model approach. We will primarily focus on the second approach, which is the pre-trained model approach. Now, in a developed model approach, we develop a model that is better than a naive model to ensure that some feature learning has been performed. Reuse and tune the developed model for the task of interest. So first we will have a naive model, then we will develop a model which is better than the naive model, and we will reuse and tune this better model for a task of our interest. And the second approach is the pre-trained model approach, where we select a pre-trained source model from available model to reuse and fine-tune. For example, as you can see in the develop model approach, there are 4 steps: select source task, develop source model, reuse the model, and tune the model. Whereas if you look at the pre-trained model approach, there is only 3 tasks: select source model, reuse the model, and tune the model. So the task develop source model is absent when we are using a pre-trained model approach. So as I have mentioned, we will be concentrating more on this pre-trained model approach. So what is a pre-trained model? A pre-trained model is a saved network that has been previously trained on a very large data set, typically on a large-scale image classification task. So one can use this pre-trained model as it is, or use transfer learning to customize this model to a given task. So I can summarize some of the usage pattern of a pre-trained model as it can be used as a classifier. That means I'm directly using the pre-trained model or for my new task, and I'm using it as a classifier itself. And the remaining 3 approaches are where we customize our pre-trained model and use the transfer learning to customize this pre-trained model on a given different task. So we have the standalone feature extractor. It can be used as an integrated feature extractor, and it could be used as weight initialization or for weight initialization. So let us look at some coding examples where I will be using pre-trained models. So we already discussed that the transfer learning refers to the process where a model trained on one problem is used in some way on a second but a related problem. In deep learning, transfer learning is a technique whereby a neural network model is first trained on a problem similar to the problem that is being currently solved. One or more layers from the trained model are then used in this new model trained on the problem of our interest. So definitely using a transfer learning has the benefit of decreasing the training time for a neural network model and can thereby result in lower generalization error. So Keras library provides access to a number of top performing pre-trained models that were developed for image recognition tasks. And these can be available by the application API. So the first time a pre-trained model is loaded, your Keras library will download the required model weights and it will be stored in your computer. And of course, when you use it or when you want to use it for the next time, this pre-trained model weights will now be loaded from your computer. So let us get started and first load the VGG16 pre-trained model that is available in the Keras library. So as we all know, VGG16 model is developed by the Visual Graphics Group at Oxford. And by default, this model expects color input images to be rescaled to a size of 224 cross 224. And we can load this VGG model from the Keras library by using this code. So you could see model is equal to VGG16. So this will directly load your VGG16 pre-trained model from your Keras library. So running this pseudo code that is shown here will load your VGG16 model and download the model weights. This model can then be used directly to classify an image into one of the 1000 classes. And the reason 1 out of the 1000 classes is because we know this VGG16 model is originally trained on an ImageNet dataset which has 1000 labels. So if you are trying to classify a image that belongs to any one of these 1000 classes, we can directly use this VGG16 model as a classification model or for the purpose of a classifier. So when I run this code, I will have, as you can see, my VGG16 model will be downloaded. The weight of the VGG16 model will be downloaded in my computer, and since I have asked also to print the summary of my model, you can see the summary and you could see the total number of parameters. Now let us go ahead and use the loaded pre-trained VGG16 model as a classifier. So remember, there are different ways in which you could use a pre-trained model, and in this example I'll be showing how to use this VGG16 model that we have just downloaded, whose weights we have just downloaded, how it could be used directly as a classifier. Now remember, the VGG16 was trained on ImageNet dataset, and the ImageNet dataset has 1000 classes. So I can actually classify directly any of those objects which belongs to these one of these 1000 classes in my ImageNet data set. So first I will need to load and reshape my image to a 224 cross 224 square, as that is expected by our VGG16, and then of course I convert that it into a NumPy array. I reshape my image and I do the pre-processing of or the scaling of my image. So these 4 steps makes my image appropriate to be loaded into a VGG16 model. So after that, you could see I have loaded my pre-trained VGG16 model, after which I will do my prediction. So the VGG16 model can now be used to make the prediction on the image that I will be providing. So let us go ahead and run this code and see what the result is. So you could see that I got the result as the classification of the image that I have given to be a treat frog with a probability of 33.48. So this was the image I asked my VGG16 to classify, and it correctly identified this as an image of a frog with a probability of 93.5. So as you can see in this code, I have not built any architecture, right? You cannot see a convolution operation or a pooling operation I have done, right? Because in this case, I am not building my own architecture. I am not training my own weights, but instead I am directly using the weights that is available in my VGG16 pre-trained model, and that is directly available in my Keras library. Now you can do the same for inception model. So here I have loaded my inception model, or you can directly load a ResNet model from your Keras library and use it as a classifier.